Imagine for a second that you're an oncologist. You are treating a patient with breast cancer, and you've just infused them with billions of state-of-the-art, genetically engineered cancer-fighting T cells.
Right, the absolute bleeding edge of medicine.
Exactly. This is revolutionary and highly expensive. But when you check that solid tumor a few days later, you find something just incredibly disheartening. Out of the billions of microscopic assassins you sent in, only 0.1% actually made it inside the solid tumor.
Yeah, 0.1%.
So where did the rest go? Well, they got completely lost. They circulated away and just ended up stuck in the bone marrow and the liver.
It is a staggering failure rate. And, that isn't some hypothetical scenario. That's a startling, real-world clinical case from the text we are unpacking today.
And it perfectly illustrates the monumental challenge of treating solid tumors. Welcome to the Deep Dive. Our mission today is to unpack a massive, cutting-edge 2026 review from the journal Cancer Cell by Chen and colleagues.
It's essentially a masterclass on the future of cellular immunotherapies.
It really is. We are going to break down why that 0.1% failure happens and look at the incredible, almost sci-fi ways scientists are trying to fix it. We'll go through the biological roadblocks first and then hit the real-world clinical hurdles. And don't worry, we'll do quick recaps along the way so you don't miss a thing.
Sounds like a plan. And to really grasp why that breast cancer case is so shocking, we have to look at the baseline. We have to look at how cell therapies like CAR-RT have performed in a different arena, blood cancers.
Because there, it's a completely different story.
Completely different. For hematologic malignancies, so leukemias and lymphomas, these therapies have been a miraculous success. We're talking about treating 40 to 45,000 patients with approved products like Kymriah and Yescarta.
Right, but in the blood, it's essentially a liquid battlefield. The engineered immune cells just circulate, and they inevitably bump into the cancer cells. It's close quarters combat.
Finding the enemy is easy, but solid tumors, breast, brain, pancreatic, they are completely different beasts. They aren't just floating targets, they are fortified castles.
They build walls and dig moats. Before we talk about how to breach those castles, let's categorize the arsenal researchers have. In this review, the tools are broken down by the cell source and the cell type. First, you have autologous therapies. That's using the patient's own cells.
Which is safe from immune rejection, but custom tailoring a therapy for every single patient is painfully slow and astronomically expensive.
Right, so the alternative is allogeneic therapies.
Yes, using cells from a healthy donor. The huge advantage is they are off the shelf. The patient comes in, treatment is ready, but you risk immune rejection or worse, graft versus host disease, where the donor cells attack the patient.
And within those sources, there are the big three modalities. First, adoptive cell therapy, taking actual immune soldiers, T cells, NK cells, macrophages, upgrading them, and sending them to attack.
Second, you have cellular cancer vaccines. This uses engineered cells, like dendritic cells or B cells, to act as biological wanted posters to train the patient's existing immune system.
And finally, stem cell therapies, using HSCs or iPSCs to deliver payloads or grow into fresh immune cells. So we have the tools. Let's get into the first functional battle, getting in and finding the target, trafficking.
Trafficking is brutal. Back to the castle analogy. The blood vessels feeding a solid tumor are wildly abnormal. A normal blood vessel is like a highway with specific off-ramps adhesion molecules that let immune cells exit into the tissue.
But tumor vessels lack these off-ramps.
Exactly. The engineered cells just speed right past. And if they do crash off the highway, they hit a physical wall, the extracellular matrix, or ECM, and cancer-associated fibroblasts.
I think of it like trying to drive an army tank through a dense, muddy, unmapped forest.
While the forest actively lies to you, tumors broadcast mismatched chemokines, chemical decoys that lead your tanks away from the battle. That's why those cells ended up in the liver.
So how do we fix the navigation?
By engineering specific chemokine receptors into the therapeutic cells like CXCR1, 2, or 3. It's a chemical GPS that ignores the decoys. Scientists are also injecting tumors with a vaccinia virus that dropped a massive chemical beacon, CXC11, painting a bullseye on the tumor.
But they still have to cut through that muddy forest.
Right, so they arm the CRT cells with enzymes like heparinase and hyaluronidase. They literally give the tanks microscopic chainsaws to chew through the ECM walls.
Okay, the GPS works, the chainsaws cut the wall, they breach the castle. Now, recognition, friend or foe. This brings up on target, off tumor toxicity, OTOT.
It's a huge problem. We train cells to look for tumor-associated antigens, or TAAs, like HER2, B7H3, or GD2, but these flags are also on normal tissues, just in lower amounts.
So if you aren't careful, the cells destroy healthy organs. You ideally want a neoantigen, a totally unique tumor barcode.
Yes, but tumors are heterogeneous. Take glioblastoma. There's a target called EGFRV8, but it's only present in roughly 24 to 67% of the tumor cells.
Target just that, and half the tumor escapes and regrows.
Exactly. So scientists are installing Boolean logic gates into living cells to make complex decisions. It's wild. Like the AND gate using systems like SNOTCH or LNK.
Where it needs two signals to fire.
Right. It requires two different antigens to unlock the kill sequence, like two keys for a nuclear launch. A healthy cell might have one flag, but rarely both.
And for the heterogeneity problem, they use OR gates.
Bivalent CARs targeting CD19 and 20, or EGFR and IL-13R alpha 2. They kill if either flag is present, casting a wider net.
But my favorite is the NOT gate. ICARs using PD-1 or CTLA-4. If the cell sees the tumor flag, it preps to attack. But if it also reads a healthy tissue flag, the NOT gate flips and physically turns the cell off. Okay, time for our first mini recap, bullet point summary for you. To beat solid tumors, we have to engineer chemical GPS to get past the physical walls and install Boolean logic gates so the cells only trigger when the exact right barcode is read.
Perfect summary.
So here's a question for you, the listener. If you were programming a microscopic assassin, what two signals would you require to flip the switch? Think about how specific you'd need to be.
You'd want to be incredibly precise, because once they are in, they face the next nightmare, surviving the swamp.
Right. Segment 2. Persistence and resistance. The tumor microenvironment, or TME, is horribly hostile.
It's an acidic, hypoxic, nutrient-depleted wasteland. The tumor is eating all the glucose. When immune cells enter, they hit a state of exhaustion. Their batteries just die.
So we need cells with better endurance.
We need stem-like memory T cells, TSCMs, and central memory cells, and we build them by pre-treating the cells with specific cytokines IL-7, 15, 18, 21, or interferon gamma for macrophages.
But you also have to rewire their engines, right? Metabolic reinforcement.
Absolutely. Since there's no glucose, researchers go into the genetic code to boost things like PE, ultra-potassium efflux, and push the cells to use oxidative phosphorylation, or OXPHOS, and fatty acid oxidation.
Converting a sports car into a wasteland off-roader.
Exactly. They knock out specific regulatory genes to prevent exhaustion, things like a Regnase-1 deletion or overexpressing c-Jun and FOXX01. They are doing ResR2 knockouts or deleting epigenetic regulators like DNMT3A to keep the cells aggressively locked in the on position.
But the tumor isn't just sitting there. It fights back through resistance.
It does. First, intrinsic resistance. The tumor literally shapeshifts. Antigen loss occurs in 30 to 70% of CD19 CAR-T patients. The tumor drops the flag.
Or it changes its entire identity.
Lineage switching. B cells turning into myeloid cells, or epithelial mesenchymal transition in pancreatic cancer. The tracking mechanism becomes useless.
And then there's extrinsic resistance.
The tumor acts like a mastermind. The hypoxia drives it to secrete TGF-beta and IL-10, which recruit suppressive cells like TREGs and NDSCs. These traitorous cells secrete chemicals that paralyze our engineered assassins.
So how do we fight a brainwashed immune system?
With armored cells. We engineer them with mutant TGF-beta receptors, dominant negative receptors, that act as a shield against the paralyzing poison.
And they can fight back, right? By secreting their own chemicals.
Yes, they become localized drug factories secreting pro-inflammatory cytokines like IL-12 and IR-15 and bispecific T-cell engagers, or BiTEs. They literally remodel the TME swamp into a supportive environment.
Time for our second mini recap. Bullet summary. Tumors drain immune cells' batteries and literally shapeshift to hide. In response, scientists are genetically rewiring immune cells' metabolisms and giving them armor that turns tumor poison into power.
It's a total arms race.
So here's a question for you. Imagine a disease that changes its disguise the moment it's spotted. How would you track it? You have to build a system that anticipates the shift, which brings us to a really scary point. Toxicity.
Segment 3, making these cells hyperaggressive is incredibly dangerous.
If I'm a patient, I'm terrified of this unstoppable army going rogue.
And you should be. The immune storm is real. Cytokine release syndrome, or CRS. Then there's ICANS, which is severe neurotoxicity. ICAT, which is hematotoxicity, and IEC-HS, a severe HLH-like inflammatory syndrome.
These are driven by massive spikes of inflammatory chemicals, specifically IL-6 and IL-1.
Yes. When the cells engage, it's a biological explosion. Doctors use targeted medical interventions, tocilizumab to block IL-6, anakinra to block IL-1, and heavy corticosteroids.
But those are reactionary. The text talks about proactive solutions.
Like pegylation, coating the cells to buffer the reaction, or implanting subcutaneous IL-6 sponges to quietly soak up the excess cytokines before a storm even starts.
But what if the cells themselves mutate? What if iPSCs form teratomas? Sponges won't stop a rogue multiplying cell.
Which is why we install remote control safety switches. Suicide genes.
The kill switch.
Exactly. First gen are chemical. ICAS9 is triggered by a specific drug, or the HSV-TK system using Ganciclovir, but that targets dividing cells generally and can cause unwanted immune reactions. Or ADCC switches.
But the next-gen switches use physical triggers.
Optogenetics is one, triggered by light, but light doesn't reach deep tissue well, so the breakthrough is ultrasound-activated switches.
This is wild. Beaming sound into the body to kill a cell.
Using MRI-guided focused ultrasound, it heats up a tiny specific area deep in the tissue. The engineered cells have a heat shock promoter, so when they feel that exact temperature spike, the kill switch flips.
But the holy grail is the autonomous system.
Radars, RNA sensors built into the cell that self-regulate. If the cell detects it's multiplying out of control or off target, it triggers its own self-destruct without any doctor intervening.
Okay, mini recap 3. Bullet summary. We can cool down immune storms with targeted antibody drugs, and we are literally installing remote-controlled kill switches activated by light, sound, or the cell itself into living medicines.
It is pure science fiction made real.
So listener, question for you. If you had engineered cells living in your body, would you want a chemical kill switch or an ultrasound trigger? I know I'd want the ultrasound. It just sounds so precise.
Definitely the ultrasound. But moving to segment 4, all of this science fiction has to meet real-world logistics. Translational challenges.
Right, manufacturing. How do we actually make these things for a patient who doesn't have time to wait?
Ex vivo expansion, taking cells out, modifying them in a lab, and growing them is slow, insanely expensive, and variable. Open manual workflows invite errors.
The reviews suggest closed automation, 3D culturing, and CRISPR editing to speed it up.
Yes, but the massive breakthrough is in vivo CAR engineering.
Bypassing the lab completely.
Exactly. Injecting viral vectors or nanocarriers directly into the patient. The patient's own body builds the CAR-Ts. It skips the lab entirely.
And there are twin cell strategies too.
Right. Combining an off-the-shelf allogeneic cell for immediate attack with a custom autologous vaccine that builds long-term memory over time.
And once we make them, administration is tricky. Systemic RNA delivery gets them lost or causes severe off-target issues, like the colitis seen in early anti-CEA trials.
So we use locoregional delivery, hepatic artery infusions for liver tumors or intraventricular catheters directly into the spinal fluid for GBM.
And to keep them there, scientists encapsulate the cells in hydrogels or APA microgels. They just pack them into a gel and stick it on the tumor.
It acts as a slow-release staging ground.
Finally, monitoring. We have to track them.
We can't just rely on MRI because of pseudoprogression. The tumor swells with inflammation and looks bigger even when it's dying. So we track them using PET and CT scans by giving the cells reporter genes like HSV-TK or NIS.
They literally light up on the scan.
Real-time tracking. And we monitor the actual disease progress with liquid biopsies, looking for cell-free DNA or CSF vesicles in a simple blood draw.
Time for our final mini recap. Bullet summary. The future is moving away from bespoke, expensive lab setups to delivering genetic instructions directly into your body and tracking the battle in real time through a simple blood draw.
A total paradigm shift in logistics.
So, listener, think about the timeline. If we can bypass the lab entirely, how many more lives could be saved when days matter, when waiting 3 weeks for a lab just isn't an option?
It would democratize the entire field of cellular therapy.
It really would. As we synthesize all of this, a massive picture emerges. We are watching the evolution of medicine. We are moving away from blunt instruments like chemotherapy that just poison everything.
We are entering the era of smart, living, adaptive medicines. These cells can think, they can navigate physical barriers, they compute Boolean logic, and they adapt to resistance in real time.
It's an unprecedented convergence. Material science, AI predicting neoantigens, synthetic biology. And I want to leave you, the listener, with one final provocative thought.
The autonomous systems really open up a wild future.
They do. We've talked about programming these cells to fight and giving them kill switches. But with AI and systems like radars, allowing cells to autonomously monitor our bodies without human input, what happens when we create a permanent roaming immune police force inside us?
A synthetic immune system.
Exactly. Someday, your engineered immune system might be vastly smarter and live much longer than the diseases it was built to fight. If it catches every mutation before it becomes a tumor, what does that mean for the future of human longevity? Could a synthetic immune system eventually allow us to outlive our natural biological limits?
It's the ultimate preventative medicine.
It changes what it means to be human. Something for you to ponder. Thank you so much for joining us on this deep dive. Keep questioning and keep exploring.